Good evening, everyone. Thanks so much for joining us tonight. My name is Serena Longo, and on behalf of Harvard Bookstore, the Harvard Division of Science, and the Cabot Science Library, I'm very pleased to welcome you to our program tonight with Marcia Bartusiak, discussing her new book, Dispatches from Planet 3, 32 Brief Tales of the Solar System, the Milky Way, and Beyond. In just a moment, I'll turn you over to Melissa Franklin of the Harvard Physics Department, who will be introducing the program this evening. But first, I'd like to take a quick moment to tell you about the Cabot Science Book Talk, a new collaboration between the Harvard Division of Science, the Cabot Science Library, and Harvard Bookstore. This series features talks throughout the academic year by authors of recently published books on a variety of science-related topics. Our next Cabot Science Book Talk will feature Adam Becker discussing his new book, What is Real? The Unfinished Quest for the Meaning of Quantum Physics, right here at the Harvard Science Center on November 15th. To learn more about this and Harvard Bookstore's many other upcoming events, visit us online at harvard.com and sign up for our weekly email newsletter as well. Tonight's talk will conclude with some time for your questions, after which we'll have a book signing and reception with refreshments in the Cabot Science Library just outside this room and across the hall. We have copies of Dispatches from Planet 3 for sale in the library at the reception. As always, you have our thanks for buying books from Harvard Bookstore. Your purchases truly support this author series and ensure the future of a local independent bookstore. So as always, thank you. And finally, a quick reminder to silence your cell phones for the talk. And so now, to introduce our speaker this evening, I'll turn things over to Professor Melissa Franklin.
Hi, that was so professional. I feel like it was really good. I really like that. So how many people here are not from Harvard? Oh, nice. Thank you. Thank you so much for coming here. I like it very much when you come here and then we tell you things. So I'm very excited about this. I learned about Marcia Bartusiak a long time ago because I'm a scientist. I'm a particle physicist. And most scientists, many scientists, not most, don't exactly know how to write perfectly. And Marcia actually teaches scientific writing. At MIT, she's the professor of the practice in the graduate program in science writing. And professor of the practice means someone who actually professes what they practice. I teach waves, but I don't do them. Anyway, I've always wanted to take her course, and one day when I get old enough, I'll have time. It never happens, says my 89-year-old colleague. So unfortunately, when I was looking up Marcia's or Professor Bartusiak's bio, I saw so many awards that I started feeling very small, very, very little. She's an incredibly accomplished science writer. She's won many awards from the American Institute of Physics, including one award which is for cultural, artistic, and humanistic dimensions of physics, sort of like the extra dimension. And she's written many books on Einstein's Unfinished Symphony, Black Hole. How can an idea banded by Newtonians, hated by Einstein, and gambled on by Hawking become loved? That's the black hole itself. I personally also love black holes. She's won prizes from the History of Science and Society, the Davis Prize. So she's part of the advancement for the AAAS. She's basically a very, very accomplished science writer. She started as a TV reporter. And apparently, as I understand, someone sent her over to NASA to do a piece, and then she just decided she would become a science writer, and she stayed at NASA. No. Yes? No. Anyhow, she did her degree in communications, and so it's kind of exciting for me to start this series of having science writers, some of whom are scientists and some of whom are not, talk about science, because what we're going to find is we're going to do a little experiment to see who's better. And I'm just betting on the science writers. So tonight we're going to hear from Marcia Bartusiak about her new book, and I'm kind of excited. Okay.
I have my own. Thank you so much, Melissa. I didn't know I'm going to be a data point now as the experiment goes on. I have been very privileged over the last 4 decades, I can't believe I'm saying that, to be covering the frontiers of astronomy. I have literally had a front row seat while there were all these new phenomena being found, discovered, talked about. For example, we all know that galaxies form clusters. And there are even clusters of galaxies known as superclusters. But in the 1980s, astronomers were very surprised to see that there was actually a pattern to the distribution of galaxies throughout the universe. And this was my one scoop in the 1980s when this pattern, the first evidence came out, right here from Harvard, actually, that galaxies look as if they're distributed on the surface of bubbles with voids in between. The universe actually is a sponge. And this organization was imprinted very early on into the plasma of the universe right after the Big Bang. So that was something that I was covering. And at the same time, there was the mystery of the dark matter, the fact that around individual galaxies and clusters of galaxies, there's this invisible material that astronomers right now don't believe is ordinary matter, the matter that makes us up, but something totally new, maybe a new particle not yet discovered. And also, I was witness to these wonderful new instruments coming into astronomy, including the laser interferometer gravitational wave observatories. This one in Louisiana, and its mate is in the state of Washington. And you may have heard in the last few years how they are literally sensing the vibrations of space-time from violent events in the universe, black holes and neutron stars colliding. And I was there as they were constructing it, and I wrote a whole book about it. My Einstein's Unfinished Symphony was about LIGO and coming to build this great new detector, which is the most sensitive instrument in the world. And in fact, here's an image of those space-time ripples emanating from 2 black holes colliding. Those gravitational waves are literally space-time stretching and expanding, stretching and contracting, as they go through the universe at the speed of light from these great events. But the last 10 years, I've actually also been dipping more into history. Maybe that 40 years, I felt like I finally had some perspective and I could provide some overview to all these new discoveries. So I started going over into another little branch. I wrote a book on the history of modern cosmology, the birth of it in the 1920s, the history of the black hole. And with this new book, I'm actually starting to meld these 2 new enterprises. I would take a new finding, new idea that hit the headlines, and I'd sort of pull back and provide the backstory on these various events. For example, when Pluto was demoted to dwarf planet in 2006, it reminded me this actually happened before. You may not know this, but it is in my book. When Ceres Pallas, Juno, and Vesta were discovered in the 19th century, right past Mars. They were listed in the textbook as full planets. They reigned as planets for a while, until they sort of came to the understanding, well, they were much smaller, and they were part of this larger entity called the asteroid belt. So just as Pluto is now considered one of the larger members of the Kuiper belt, so too were these objects part of the asteroid belt. Although, and we have someone in the audience who may talk about this, there's a campaign to put Pluto back into the solar system. And then also, when there was evidence building up that there is or was water on Mars, as seen here in these gullies that you see carved into the side of this crater, it made me think of this man, Percival Lowell, who made the question of water on Mars so famous at the turn of the 20th century. Lowell was a Boston Brahmin, one of those Lowells, and with all his wealth, he decided to build his own observatory in Flagstaff, Arizona. His obsession was the planet Mars, and he was inspired by an Italian astronomer whose name was Giovanni Schiaparelli, who had earlier detected some streaks on Mars, and in Italian he called them canali, which in Italian means channel. Now, Schiaparelli thought it was just some geologic process, but of course, with the name canali, a lot of people started thinking, canal. Ooh, alien beings are building those canals on Mars. Well, that idea started spreading, and Lowell was the champion, the biggest champion of this vision. And so I'd like to tell that story, read this from my book. With the opening of his observatory in 1894, Lowell immediately began to map Mars, adding 116 waterways to Schiaparelli's original depiction. The lines discerned on Mars, he declared, were assuredly artificial rivers conveying seasonal snowmelt from the planet's polar caps. That they were even visible from Earth was likely due to the massive vegetation growing along the canal banks. Promoting his ideas in books and lectures like a blue-blooded carnival barker, he fancifully imagined his Martian civilization as dependent on its global irrigation system to remain extant. The very fact that the Martian features he saw were straight, like the canals, streets, and railways on Earth, increased the odds, he claimed, that they were produced by intelligent workers. Serious astronomers were aghast at Lowell's certainty. Prestigious scientific journals refused to publish his findings. William Wallace Campbell, then director of the Lick Observatory, the Lowell Observatory's chief competitor, called Lowell a trial to sane astronomers. Many other observers were not seeing the same Martian features, and with good reason. From Earth, the surface of Mars was, and still is, notoriously difficult to make out. Even under excellent conditions for seeing, Mars shimmers tantalizingly, allowing only fleeting glimpses of its surface. Lowell had clunkily collated his overall map from dozens of sketches of individual Martian regions, each glimpsed in a flash. The public and the popular press, however, reveled in Lowell's story, so much so that by 1907, the Wall Street Journal reported that evidence for the existence of Martian folk surpassed that year's financial panic as the news story of the year. That media endorsement, though, was Lowell's last hurrah. Within a few years, making further observations with larger telescopes, astronomers generally concurred that Lowell's canals were merely an optical illusion, the eye imposing linearity upon an array of smaller, irregular details. The Boston Brahmin's exotic imaginings were finally put to rest once and for all when a series of Mariner missions launched by NASA in 1965 and 1969 showed Mars to be a completely barren world pitted with craters. Intriguingly, though, Mars orbiters later photographed ancient riverbeds with tributaries and erosion patterns that appeared to be carved by catastrophic flooding episodes. Perhaps Lowell would have been elated that there were Martian channels after all, but these passages were forged by water flowing naturally and in Mars' distant past rather than in the present day. In the end, to Lowell's likely dismay, there were no little green men digging trenches. Well, the essays from my book were written over a number of years, each sparked by something that was in the news that month. And I had no really special agenda. I just let the news carry me along. But it was a real thrill when I was putting this collection together, where I realized all the number of women in my essays that were involved in some of astronomy's greatest moments. Many of them often not found in the textbooks, and they fill a quarter of my book. There's Jane Liu, who discovered the first Kuiper Belt object. That is the leftovers from the solar system past Neptune, and this is why Pluto got demoted. There is Margaret Burbidge, who was the woman who provided the observational evidence that the calcium in our bones, the iron in our blood, the oxygen in the air, all originated from an ancient star that died and spread those elements into interstellar space until they gathered once again to form our solar system and our planets, and they now reside in us. That was Margaret Burbidge. There was Vera Rubin. She is the woman who in the 1970s and 80s provided overwhelming evidence that indeed dark matter was surrounding the galaxies and clusters of galaxies. She got the whole thing going, and it's still a mystery to this day. Cecilia Payne-Koposhkin, right here at Harvard, she received the very first PhD in astronomy here at Harvard, and she was the woman who discovered that hydrogen was the major element in the universe, a million times more plentiful than the other elements. That was so controversial in 1925 that they told her to take it out of her thesis. Someone else got the credit later on. Henrietta Leavitt, also here at Harvard. This is the woman who was studying variable stars, specifically Cepheid variables. And by doing that, she discovered a pattern that provided a new cosmic yardstick that enabled astronomers to find distances much, much farther out than they had ever been able to do before. In fact, it's due to that rule, that pattern that she discovered, that cosmic yardstick that she provided, that enabled Edwin Hubble to discover that there were other galaxies outside the borders of the Milky Way. In fact, she was nominated. She did this work in the 1910s. She was nominated for a Nobel Prize. But unfortunately, the one who wanted to nominate her found out 4 years too late. She had died earlier. She died young in her 50s of stomach cancer. It would have been nice. She would have joined Marie Curie as one of the early women winners of perhaps a physics prize. And then there is Jocelyn Bell, who discovered the neutron star. In the 1960s, Bell was part of a platoon of students and technicians led by her advisor, Anthony Hewish, who built this sprawling radio telescope just outside Cambridge University in Great Britain. More than 2,000 dipole antennas lined up like rows of corn. Bell, who was a native of Ireland, liked to say that she got her thesis by sledgehammering, putting in all those poles. Actually, for her thesis, it was her job to look out and analyze the stream of paper that was coming out of those old-fashioned chart recorders. It was 100 feet each day, and it was her job to look and see if there was going to be any signals. The radio telescope was actually originally set up to look for quasars. These are very active galaxies in the far distant universe. So that was her job, and that's what she was looking at. Well, as she was looking over some of the first few hundred feet, she saw what she called a bit of scruff seen there below the arrows. And it didn't look like a quasar to her. In fact, she said, I think I've seen this before when the sky went overhead and they had recorded that same part of the sky before. So she wanted to look further into it. So again, I will read from my book to tell you the rest of this story. Eventually observing it with a higher speed recording, Bell, later Bell Burnell upon marriage, came to see that the scruff was actually a methodical succession of pulses spaced 1.3 seconds apart. The unprecedented precision caused Hewish and his group to briefly label the source LGM for Little Green Men. This was done only half in jest. At one point, some consideration was given to the possibility that the regular pulsations might be coming from an extraterrestrial-built beacon, which annoyed Bell a bit. Quote, I was then 2.5 years through a 3-year studentship, and here was some silly lot of little green men using my telescope and my frequency to signal the planet Earth. But within a few months, Bell uncovered 3 more rhythmical signals in different regions of the sky. There was no more mention of outer space aliens. It was highly unlikely, she said, that there were, quote, lots of little green men on opposite sides of the universe using the same frequency to get Earth's attention. Carefully kept under wraps, the news was finally released in February 1968. And upon discovering a pretty young woman was involved, the press went wild. Quote, one of the photographers even had me running down the bank, waving my arms in the air. Look happy, dear, you've just made a discovery. Inspired by the name of the recently discovered quasars, a British science journalist dubbed the novel objects pulsars, for pulsating stars, a label that astronomers swiftly adopted. Astronomers estimate that at least a few 100 million neutron stars now reside in the Milky Way, created over the eons since our galaxy's birth. But the first one revealed, officially known as PSR 1919 plus 21 for its celestial coordinates, will never be forgotten, not just for its discovery, but for the controversy that later surrounded it. When the Nobel Prize in Physics was awarded in 1974 for pioneering work in radio astrophysics, including the discovery of pulsars, it was Hewish who walked up to the podium, but not Bell Burnell. Hewish had been skeptical about Bell's scruff at first, believing at one point that it was either a stellar flare or man-made. It was only due to her persistence that its origin was at last revealed. At Great Britain's Observatory magazine, the editors wryly joked among themselves that Nobel now stood for Nobel. Her being a young female graduate student, in my book I say only 2 women have won the physics prize. Just this past week, we got a 3rd, so my book's already out of date. Since the first award ceremony in 1901 likely prejudiced the judges. But Bell Burnell, who went on to a distinguished career as a professor, dean of science, and president of the Royal Astronomical Society, maintained a sanguine attitude about this flagrant oversight. During an after-dinner speech at a relativity conference in 1977, she noted that the final responsibility for the success or failure of a scientific project rests with its supervisor. Quote, "I believe it would demean Nobel Prizes if they were awarded to research students, except in very exceptional cases. And I do not believe this is one of them. I am not myself upset about it. After all, I am in good company, am I not?" No, they're in good company with her. While memories of who won a Nobel Prize dim over time, Bell Burnell will always serve as the main protagonist when recounting the story of the neutron star's discovery. And in fact, she did get credit. Just a few weeks ago, she won the Breakthrough Prize, $3 million. So credit is now coming due to her, which she gave away for scholarships. Yes, she didn't keep a penny. I also enjoyed the story of Beatrice Tinsley, who I like to think of as the Darwin of astronomy. She was the first to show how galaxies can evolve. Up until the 1960s, distant galaxies were thought to not change too much. There was the idea that right after the Big Bang, the galaxies formed, and they just sort of glided along with the expansion of the universe, not changing that much, looking pretty much like the Milky Way today. And in fact, they used that idea because they said, well, if every galaxy has about the same diameter, the same brightness, we can use them as standard candles. You can see how a galaxy gets smaller and dimmer into the distance, and you can then measure the rate of expansion. And back then, in the 50s and 60s, they were very concerned with the question is, will the expansion end? Is the expansion slowing down, that at some point the galaxies are going to stop and then gravitationally come together back into a big crunch? That was the big question in cosmology back then. And Beatrice came into this through the side door. She actually majored in solid-state physics. That was her master's degree. And she and her husband then moved to the United States, and she wanted to continue on for her PhD, but not in solid-state physics. She wanted to switch to cosmology. Kind of a difficult thing to do because most departments, in astronomy departments is, what are we going to do with a solid-state physicist? But University of Texas at Austin took a chance. They liked her record, so they decided to bring her on, and she wanted to join that campaign to find out if the universe indeed was at some point going to close back up. So she started looking at all the parameters, the magnitudes of galaxies, the diameters. But then she had this nagging question in the back of her mind. She says, what if galaxies change over time? Well, then if that happens, if they get brighter or dimmer over time, they can't be used as standard candles. All bets are off. How are you going to carry out your experiment? So here's from my book on what she did. At that point, Tinsley chose the problem that became her dissertation, actually simulating the evolution of a galaxy. Setting up a numerical model, she would track its changes in color and brightness over billions of years as the stars within it are born, fiercely radiate, and then inevitably die. It was an ambitious task, as numerical simulations were grueling in this primordial era of computing. No one before had ever tackled such a problem in great detail. It has been described as one of the boldest graduate thesis projects ever undertaken. Tinsley had to set up an initial population of stars and then decide how quickly they would die and how soon new stars would be generated to take their place. After her dissertation was completed in 1967, she continued to refine her models over the years, each simulation concluding that galaxies can undergo substantial evolution through time, far more than astronomers had previously thought. A young galaxy starts out bright and blue when its resources of gas to form stars are at their peak, and then gently reddens with age and dims considerably as the stars age and die over the eons. Some more senior authorities at first took issue with these conclusions, but eventually her findings encouraged observers to start pushing outward with their telescopes to discern her predicted galactic evolution firsthand. As a consequence, Tinsley's papers began to be cited in dozens of scientific publications. Yale University took notice in 1975 by offering her a professorship, a post she had been unable to secure years earlier, to her great frustration, in either Texas or elsewhere. The woman once regarded in Dallas as Brian Tinsley's clever wife, rather than as a scientist in her own right, according to science historian Joanne Eisberg, had proved that people had vastly underestimated her talent. All those efforts ushered in a new era in extragalactic research. I should point out, every dot in this picture is a galaxy. There's not a star in it. It's all galaxies. Faraway galaxies that had been smudges in Hubble's day are being viewed today with impressive clarity. And what astronomers are seeing is that galaxies over time can exhibit diverse personalities. Some do move serenely through the cosmos, evolving internally, as Tinsley calculated, but astronomers now know that many can also change more recklessly. Galaxies may collide, merge, sideswipe one another, or gobble up unwitting passerbys. Sadly, Beatrice Tinsley witnessed very little of the new era she inspired. In 1978, a lesion on her leg was diagnosed as melanoma, a malignant skin cancer. While continuing to teach and carry out research, she underwent extensive radiation and chemotherapy, but ultimately the treatments were unsuccessful. She died in March 1981 at the age of 40. Writing in Physics Today a few months later, Sandra Faber of the University of California, Santa Cruz, observed that Tinsley had changed the course of cosmological studies. 2 weeks before her death, while hospitalized in the Yale Infirmary, Tinsley submitted her last scientific paper to the Astrophysical Journal. No longer able to use her right hand, she had written it with her left. The article advanced her work on galaxy evolution and was published the following November without revision by the editors. There was also another theme that I noticed when putting my collection together, and that is the tricky nature of who gets credit for a discovery and a finding. For example, in 1929, Edwin Hubble published this famous graph showing how galaxies are moving outward in a regular fashion, now known to be the evidence for an expanding universe. This was the graph that was literally heard by astronomers around the world. It displays the distance of a galaxy there along the horizontal axis versus a galaxy's velocity there along the vertical axis. And the interesting thing is, Hubble had done all the distance information, but all that velocity information, little bug here, all that velocity information was done by someone else, Vesto Slipher, an observatory from Lowell Observatory. In 1913, Slipher started measuring the velocities of what were then known as spiral nebulae. And in 1913, he found that the Andromeda Nebula was traveling at 300 kilometers per second. He continued in this work, and by 1917, he had 25 velocities of these spiraling nebulae, some as much as 1,000 kilometers per second. And actually, in 1917, by then, he was pretty sure that they were galaxies. But he couldn't know for sure because they didn't yet have distances to these nebulae. He had the velocities. It was Hubble in 1924 who began making the distance measurements to these galaxies. So finally, in 1929, Hubble put these two bits of information together, his distance information and Slipher's velocity information. And we now know that the rate of expansion is the Hubble constant. But Hubble did not give credit at all in his paper to Slipher in that paper. He didn't say a word that the velocity information was coming from Slipher. So instead of the Hubble constant, I think it should be the Hubble-Slipher constant because it was two sets of data coming together. And actually, the story gets even more complicated than that because, there's Slipher. I should have brought him up earlier. It's a little more complication because of this man, Georges Lemaitre, who was a Belgian cleric and a mathematical physicist. And 2 years before Hubble did his famous paper, he also came up with a rate of expansion. In fact, with this paper, published in 1927, 2 years before Hubble, he said that the receding velocities of the extragalactic nebulae are a cosmical effect of the expansion of the universe. He is actually the one who first knew and discovered that the universe was expanding. Unfortunately, he published this in an obscure Belgian journal that no one read, and he was a little reticent. He didn't go out and talk his idea, so no one heard about it. It wasn't until 1930 that this paper was translated and published in the monthly notices of the Royal Astronomical Society in Great Britain, and then finally everyone knew that indeed the universe was expanding. In fact, there's now a campaign on from the International Astronomers Association to give Lemaitre credit for the expanding universe. And I'd like to continue my campaign for the Hubble constant to be called the Hubble-Slipher constant. And then there's the case of the cosmic microwave background, the wash of radiation that surrounds us today, the leftover radiation from the Big Bang. It started very energetically as gamma rays and X-rays, and then as the universe expanded and space-time stretched, that radiation also stretched its wavelength into today the microwave range, short radio waves. So who first figured this out? Well, if you read the standard textbook, you'd say it all happened in the 1960s. But it actually first came out in 1948 due to Ralph Alpher and Robert Herman, who worked with the physicist George Gamow on the evolution of the universe. And here is from my book on how that Sometimes a great scientific idea needs time to take root. Sometimes the world simply isn't ready. Continental drift comes to mind as an example, as well as germ theory. Continents moving about, microscopic bugs. Each of those propositions, when first proposed, seemed too bizarre to accept right off. In such situations, scientists have to be convinced that a new concept is worth looking into. Astronomy is no exception. A famous case is a prediction of cosmic proportions that first appeared in a 1948 scientific paper almost as an afterthought and was soon forgotten. Decades passed before the dismissed conjecture turned into cosmology's greatest tool. This result was revealed in an unusual manner. On October 30th, 1948, George Gamow published an article in the British journal Nature titled The Evolution of the Universe. But in checking over Gamow's reported results, Ralph Alpher and Robert Herman found some errors. They soon dashed off a correction, seen here, a brief letter to the editor, barely 4 paragraphs long, that was published within 2 weeks. With their more accurate figures, Alpher and Herman showed how the density of matter and the density of radiation changed as the universe evolved. In doing so, they curtly noted at the end of their letter that, quote, "There seen in pink, the temperature in the universe at the present time is found to be about 5 degrees Kelvin. That's only 5 Kelvin above absolute zero, the point at which all motion ceases." With little fanfare, Alpher and Herman were telling the world that the present-day universe is bathed in a uniform wash of radiation left over from the flood of highly energetic photons released in the fury of the Big Bang. Cooled down now over the eons with the expansion of the cosmos, the waning fire now surrounds us as centimeters-long radio waves. Today it is known as the cosmic microwave background. When their note was published, the Big Bang theory was still highly controversial. Many astronomers preferred the steady-state model of the universe, a theory that postulated that space-time had neither a beginning nor an end. But Alpher and Herman's calculation was a clear-cut means of deciding between the two opposing theories of the universe's behavior. Yet no one followed up. Looking back, it's hard to fathom why astronomers in the 1950s didn't jump at the chance to point their instruments at the sky and capture this primordial whisper of creation. But some thought radio telescopes weren't yet sensitive enough for the task, and when a few astronomers did peg an overall temperature of interstellar space at around 3 Kelvin, they didn't link it to cosmology at all. In fact, some of them thought it was an error in their instruments. The radio sky was also new. There were too many objects, radio stars, radio nebulae, radio galaxies grabbing their attention. Amid such distractions, Alpher and Herman's prediction was either dismissed or utterly overlooked. And since both men later went into industrial research, the two didn't have the opportunity to keep pushing astronomers to take a look. Although they did try, at one point, even holding a press conference to generate attention, but to no avail. The idea didn't resurface until the mid-1960s, when a team of astrophysicists at Princeton University and some Soviet cosmologists independently again reasoned that the Big Bang's residual heat must be permeating the universe. At the same time, 2 Bell Lab researchers in New Jersey, Arno Penzias and Robert Wilson, accidentally detected what proved to be the primeval microwaves. They were trying to eliminate excess noise in a horn antenna they were calibrating for astronomical work, but a stubborn residue always remained. Once Penzias and Wilson learned of the Princeton team's work, they at last understood that their radio interference was cosmic. In 1965, the two groups published papers simultaneously in the Astrophysical Journal. Neither paper mentioned Alpher and Hermann's earlier contribution. For detecting the cosmic microwave background radiation, Penzias and Wilson received the 1978 Nobel Prize in Physics. Hermann died in 1997, Alpher 10 years later. Both were deeply pained that the career rewards for making their momentous prediction never came to pass for them. And so the credit remained unsaid. Well, there are 32 such stories in my book. I hope by presenting a few of these, I have tantalized you for wanting to dip into more. I thank you for coming, especially since this is such a crucial night for the Red Sox. So I hope you have an interest in dipping into my book further. And I am ready to take some questions if you have any.
Thank you. That was really great. The good thing that scientists get pleasure in just doing science, so we're not too sad. We're not too sad about not getting credit. Yes, but we have lots of questions, and we have two people with microphones, and we have a ball. Hold on.
I love it.
Okay. Tax.
Oh, I hear you.
I do love all the stories you just
Closer so everyone can hear.
I do love these stories you just read for us. And my question is, because I noticed all the stories are something happened in stories. So do you have a time span for all these 32 tales?
They generally range. Well, I do mention the Greeks in a few places, so you can say I go from Aristotle to the current day. So they do the whole range.
So which one is the most updated one?
Which is the most updated?
1970 or?
I'm trying to think. I've already have one error in the number of women who have won Nobel Prizes. I would say the chapter on Einstein's symphony, in which I talk about the gravitational wave astronomy results, is some of the latest.
1970? I'm right.
Yeah, the first detection was in 2015, and they are continuing now to gather their data.
Can I ask a follow-up question? Sorry. So one question you proposed intrigued me, which is who takes the credits for science discoveries? My question is, because you told some stories about the competition. So my question is, if about international cooperation, like 2002, Kobayashi. We have several, Japanese scientists made the Nobel Prize laureates.
Yes, in fact, I mentioned that the neutrino astronomer.
Yeah.
I do mention them in my book because I have a chapter on neutrino astronomy, how you can study the universe by gathering neutrinos from the cosmos. And the Japanese made a very important contribution with their detector in Japan.
That's great. I read his autobiography, and I know in a Japanese village, a group of Japanese scientists deep really a big hole and with lots of light bubbles and
Yes.
purified water inside.
Yes, an underground, yes. In order to catch neutrinos, you have to go underground, and they have these photodetectors that are seeing the neutrinos are tiny particles that can literally go right through the Earth without being caught. But every once in a while, one is. And they have this huge underground detectors, several places throughout the world where they are capturing these neutrinos.
Meanwhile, there's another team in Italy do the same thing with different constructions. All of them lots of money. So
Oh, yeah.
How do you
These are very
think
high.
fairs, computational science?
Well, I try to, as a science writer, I try to give credit where credit is due and mention all the collaborators when there's a number of collaborators. But often, for stories like this, I often like to focus on individual discoverers and finders because it makes for a more compelling story. But if there's a need to give credit, I will make sure that people know that there are other people out there also working on similar problems.
Thank you.
Way over there.
As a science writer, how deeply do you have to be able to understand the science to write about it?
Actually, you have to have more a curiosity and the ability to ask the right questions. I myself, I have a graduate degree in physics. After my TV days, I actually went back to school and got a graduate degree in physics, and I melded the two backgrounds, the writing and the science, which has helped me tremendously. But I also know some of the greatest science writers, Timothy Ferris, Richard Preston, they had PhDs in English literature, and yet they did a tremendous job in translating the science. A lot of it has to do with being able to conduct a good interview, dig deep, and work with the scientist in understanding the phenomenon. It's not our job to teach science. It is our job to find the right metaphors and analogies so people get a feel for the mechanism. And so you don't necessarily need the science background, but you need that curiosity and a willingness to keep working at it till you find the perfect metaphor.
The follow-up, where is your wall? What can you understand? If maybe you don't, but is there anything you can't comprehend, like your brain just doesn't can't quite grasp?
Gosh, I'm trying to think, anything in molecular biology. I have to really work because my background is in physics, which helps me a lot. Physics really is the foundation. I'm with those people who think you should flip the high school, start with the physics, and then work into the chemistry and biology because the physics gives you that foundation. But those specialty areas have their own language, their own jargon, and you have to be immersed in it. I have to do a lot of Googling and Wikipedia reading to sort of catch up in a layman's sort of way. So yeah, it can be hard if you're outside your comfort zone, as we like to say in our program.
Yeah, I don't understand string theory.
There you
Do you
go.
understand string theory?
Only I understand it through the metaphors and analogies.
So why do you think it is that so many women scientists, more than these actually, die so young?
Yeah, it was in this case Beatrice Tinsley and Henrietta Leavitt. It could be just coincidence. People do die young, so you're also going to have scientists die young. Henrietta Leavitt did have a condition. She was deaf as well, and so there may have been some frailty on her part. No, it may have been even hard for Henrietta Leavitt because it was many, many years later before astronomers were honored as part of the physics award. It may not have been her time.
So I heard recently that the new Nobel Prize winner, Canadian woman, didn't have a Wikipedia page because Wikipedia didn't let her have a page.
This was amazing.
Famous enough.
Did you hear that? She just won the Nobel Prize in physics, and just a few weeks before, they kicked out her Wikipedia page as she wasn't notable enough.
Well, no, I mean, I think Wikipedia is about infamousness, not about goodness at science. That's my understanding.
Well,
she
they
wasn't a full professor, which means she hadn't reached the heights hides the.
Oh, they definitely have it now.
Apparently, they needed a lot of paperwork before, but then in one day, when she got the Nobel Prize, she was able to get it without any paperwork. Anyhow, if there are no more questions, or are there more questions? That was a very nice talk, and thank you so much for giving us.
Thank you for coming.